Welcome to AI Frontiers, your guide to cutting-edge artificial intelligence research. Today, we explore the remarkable events of December 29th and 30th, 2024, when 18 groundbreaking papers emerged from laboratories worldwide. These weren't just ordinary research publications, they represented a concentrated push by brilliant minds racing against time to establish their discoveries before 2025. From spatial reasoning failures that stumped every AI model to frameworks for autonomous scientific discovery, these papers offer blueprints for the intelligent systems that will transform our world. Picture this stunning revelation: when researchers tested the latest AI models on seemingly simple spatial reasoning tasks, every single one failed completely. Not struggled, not performed poorly, failed entirely, with a 0% success rate. This wasn't a statistical quirk or measurement error. These were sophisticated systems that could write poetry, solve complex mathematical problems, and engage in nuanced conversations, yet they couldn't navigate basic spatial challenges that a child might master. This complete failure reveals surprising gaps in machine intelligence and opens a fascinating window into the complexity of cognitive abilities we often take for granted. Over the next hour, we'll embark on a journey through 18 remarkable papers that showcase the full spectrum of AI advancement. From mathematical reasoning breakthroughs that push beyond standard benchmarks to revolutionary frameworks for AI creativity, from the surprising limitations of spatial intelligence to autonomous systems that can discover new scientific knowledge. These aren't merely academic exercises confined to university laboratories, they're practical blueprints for intelligent systems that will reshape medicine, transportation, scientific research, and virtually every domain of human endeavor in the coming years. Think of the field of computer science and artificial intelligence as a vast, interconnected ecosystem. Imagine a digital rainforest where different species of algorithms, neural networks, and reasoning systems evolve and interact in complex ways. Just as a rainforest contains everything from towering canopy trees to intricate fungal networks underground, the AI research landscape spans from fundamental mathematical reasoning at its roots to sophisticated multi-agent systems reaching toward artificial general intelligence in its upper branches. What makes this collection particularly fascinating is its temporal clustering. Like a synchronized emergence of cicadas, these publications appeared within a narrow window, suggesting researchers' eagerness to contribute to the scientific discourse that would shape 2025's research directions. A significant portion of current AI research focuses on enhancing machines' ability to perform mathematical and logical reasoning. The evaluation of large language models on underrepresented mathematics competition problems exemplifies this theme, where researchers discovered that mathematical reasoning serves as a proxy for more general cognitive abilities. It's like teaching a child not just to memorize multiplication tables, but to truly understand what multiplication means and when to apply it in novel situations. Understanding where current models fail provides roadmaps for improvement, much like how studying optical illusions helps us understand human visual perception and the underlying mechanisms of cognition. The second major theme involves embodied intelligence and spatial understanding. Imagine trying to navigate your hometown while blindfolded, building a mental map from limited sensory information at each step. This captures the essence of research on how foundation model agents explore, remember, and reason in map environments. This growing focus on embodied intelligence reflects the recognition that intelligence isn't just about processing abstract information in isolation, but about understanding and interacting with the physical world in meaningful ways. The research reveals that spatial reasoning requires fundamentally different cognitive mechanisms than language processing or pattern recognition. Agent-based systems and multi-agent coordination represent perhaps the most ambitious frontier in current AI research. Think of it like orchestrating a jazz ensemble where each musician is improvising, yet they must harmonize to create something greater than the sum of their individual performances. From belief-guided exploratory inference for world-grounded embodied agents to frameworks enabling global networks of autonomous scientific agents, this represents a shift toward more sophisticated forms of artificial collaboration. The development of protocols for autonomous scientific agents represents an emerging frontier where AI doesn't just solve existing problems but actively participates in creating new knowledge. Imagine having research assistants that never sleep, never forget what they learned, and can simultaneously work on thousands of experiments while continuously improving their own capabilities. Among the many significant results presented in these papers, several findings stand out as particularly groundbreaking for the field's advancement. Research on map-based spatial understanding reveals that spatial reasoning performance hits a ceiling across model versions and scales beyond a certain capability threshold. This finding suggests that improvements in spatial understanding require mechanisms specifically tailored to spatial representation and reasoning, rather than relying on the bigger is better approach that has driven much of recent AI development. Another groundbreaking finding reveals that epistemic robustness, a model's ability to maintain factual accuracy under stress, operates independently of conventional design paradigms. Neither parameter count nor architectural type significantly predicts how well a model will maintain its knowledge when information degrades. Research on interactive reasoning tasks demonstrates that explicit graph-structured exploration can substantially outperform state-of-the-art language models in complex problem-solving scenarios, suggesting that systematic approaches can be more effective than relying solely on implicit reasoning capabilities. From this remarkable collection of cutting-edge research, one paper stands out as particularly transformative: Thinking on Maps, How Foundation Model Agents Explore, Remember, and Reason in Map Environments by Wei and colleagues. This work represents a fundamental contribution to our understanding of spatial intelligence in artificial systems, addressing a critical gap in how we evaluate AI systems' spatial reasoning capabilities. Rather than simply presenting complete maps or text-based spatial queries to AI systems, the research team designed a sophisticated framework where agents must incrementally explore grid-based environments, building their understanding through limited local observations at each step, much like how a person might navigate an unfamiliar city using only what they can see from their current location. The methodology employed in this study is particularly elegant, involving systematic manipulation of three key components: exploration strategies, memory representations, and reasoning schemes. Agents navigate environments consisting of roads, intersections, and points of interest, receiving only local observations at each step. The researchers then evaluate spatial understanding through 6 distinct types of spatial tasks, allowing them to isolate the contributions of different cognitive components. It's like conducting a controlled experiment on how different aspects of human navigation work, but with AI systems as the test subjects. This approach moves far beyond static assessments to create an interactive, experience-driven evaluation framework that more accurately reflects real-world spatial reasoning challenges. The findings of this research challenge several fundamental assumptions about how spatial intelligence emerges in AI systems. Most surprisingly, the researchers discovered that exploration strategies, while affecting experience acquisition, have remarkably limited impact on final reasoning accuracy. This counterintuitive result suggests that the quality of spatial reasoning depends more on how information is processed and stored rather than on how it's initially gathered. More importantly, the study reveals that memory representation plays the central role in consolidating spatial experience. Structured memory representations, particularly sequential and graph-based approaches, substantially improve performance on structure-intensive tasks such as path planning. But perhaps most significantly, the research demonstrates that spatial reasoning performance saturates across model versions and scales beyond a certain capability threshold, fundamentally challenging the prevailing assumption that simply scaling up models will automatically improve their spatial reasoning capabilities. Looking toward the future directions emerging from this research, several promising paths become clear. The development of more sophisticated memory architectures specifically designed for spatial and temporal reasoning appears crucial for advancing embodied AI systems. The integration of active exploration with structured memory systems could lead to AI agents that can rapidly adapt to new environments while building upon their accumulated spatial knowledge. The field is moving toward more embodied forms of artificial intelligence that can understand and interact with the physical world in meaningful ways. Perhaps most importantly, this work suggests that the future of AI may lie not in building ever larger general-purpose models, but in developing specialized cognitive architectures that can excel at specific types of reasoning while integrating effectively with other specialized systems. It's like evolution developing different types of intelligence for different ecological niches rather than trying to create one superbrain that does everything. As we reach the conclusion of our journey through these 18 groundbreaking papers, we've witnessed a field in remarkable transition. From the surprising limitations revealed in spatial reasoning tasks to the revolutionary frameworks for autonomous scientific discovery, from the emergence of self-evolving AI systems to the development of more sophisticated approaches to safety and alignment, these works collectively paint a picture of artificial intelligence research that is both more mature and more ambitious than ever before. The common thread running through all these discoveries is the recognition that intelligence, whether artificial or natural, is far more complex and nuanced than we previously understood. The 0% success rate on spatial reasoning tasks isn't a failure, it's a roadmap that tells us exactly where we need to focus our efforts to create AI systems that can truly understand and navigate our complex world. This analysis was synthesized using advanced language models to process and interpret the latest research from the archive preprint server. Text-to-speech synthesis was powered by Amazon services, while image generation utilized Stable Diffusion technology. The content has been reviewed by human experts for accuracy and clarity, though some oversights may exist. All original research references and citations are provided for verification. The goal is to make cutting-edge AI research accessible while maintaining scientific rigor and accuracy. This represents a collaborative effort between human expertise and artificial intelligence to advance our collective understanding of these rapidly evolving fields. Subscribe to AI Frontiers for cutting-edge research insights that keep you at the forefront of artificial intelligence development. Dive into these papers yourself and join the global conversation about the future of technology. Share your thoughts online and help shape the direction of AI research and development. What role will you play in this unfolding story of human and artificial intelligence collaboration? In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive preprint server content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive preprint server.